Greeting guys, so welcome back. So in this tutorial, we will be computing a sentence embeddings using the sentence transformer library. So like basically sentence embeddings are like compact numerical representation of text. So they capture like meaning, not just words. So this is what allows AI system to like measure similarities between sentences, cluster related text, and also power the search and retrieval applications. So today we will be covering a step-by-step guide to like how we can load the pre-trained sentence transform model and how we'll be encoding the text into embeddings and computing the similarity, the semantic similarities, and then we'll be using a prompt template for like specialized models. And finally, we will be seeing how we can accelerate these processes using GPUs in Google Colab. Let's start by enabling the GPU runtime in Colab. So for that, you have to go here to the runtime and then change runtime. So you have to select T4 GPUs, which is available, and then save. So you have already connected to the GPU runtime. So basically, this command, this will list all the available GPUs. Like usually that Tesla T4 or A100 or L4, yeah. And having a GPU significantly speeds up the embedding generation, which involves like matrix operations and attentions computations. So and then we will be checking the device and then we will load the model. So now let's load our sentence transformer model directly on the GPU if it's available. So we'll also confirm which device like the PyTorch detects. Okay. So we have selected the device as CUDA and we will be trying with the model all mini LM. So the base model and then we will be using GPU runtime. Otherwise, if it's not available, we will be back to CPU. Like if you see here, I have already downloaded the model. So here we are using like all mini LLM L6. So it's one of the most efficient and widely used models for like English embeddings. So it outputs like T384 like dimension vectors and automatically uses the GPU if available. If no GPU is found, it just fallbacks to the CPU. And the next step is to like compute the embeddings and similarities. So now let's see how this works in practice. Like we will encode a few sample sentences and compute their embeddings and then like measures how semantically they are similar. Okay. So you have a sample sentences I have already put in place. So with model.encode, which will encode all these in the sentence list. And once done, we have our embedding similarity, which is available in the output here. So each sentence is converted into like 384 like dimension embedding vectors. And notice that the first two sentences about like Apple and investors have like higher similarity score than the one about restaurant or like weather. So that's what we call like semantic embeddings. They capture like meaning, not just keywords. And moving on to next step, where we will be like initializing the sentence transformer models. So you can easily switch to like different pre-trained models depending on like your use cases. Lightweight ones for like speed to large one for accuracy. So the model will always use the best available device, which it may be CUDA, MPS, or GPU. Okay. So for example, here we use like our MPNet base V2, which just produces more accurate embeddings, but is slightly heavier than MiniLM that we have tried before. So you can also load a local fine-tuned model if you're trying one on like your own data. So we can load the pre-trained model like here, and then we can also it will automatically like select usually the best available device. And then let's see like the prompt template. Like certain models, especially like multilingual and retrieval oriented ones, which requires prompts to get the best performance. So prompts acts like a small task specific prefixes that like guide the model to produce more meaningful embeddings for given purpose. So if you see here in this cell, like we define like three prompt context. One is for classification, and then retrieval, and finally clustering. And set the default to retrieval. Okay, here. So this means the model will automatically prepend that frost before each input during the encoding, and also improving the embedding quality for like search tasks. So you see here we try to encode using these prefixes. And another thing that we have to keep in mind is like input sequence length. Like every transformer models have a maximum like sequence length, so which defines how many tokens it can process. So longer texts are truncated. So if you are like working with long documents, so it's better to like split them into chunks. So by default, mini LM which supports up to like 256 tokens. So here we again call our mini LM model. You can like reduce this for like faster inference. For example, it supports 256 token, so you can reduce this for fast inference, but like you cannot increase it beyond what the model supports. And then how we can adopt like multi-process and multi-GPU encoding. So finally, for like large scale embedding task, like sentence transformers about multi GPU and like multi process encoding. So this is useful if you are like encoding millions of sentences, for example, building a vector index for semantic search. So in Colab, like you usually get a single GPU, but this code is like handy when you move to like multi GPU servers or like cloud setups. So the pool like API helps in distributing the workloads efficiently and can speed up the large encoding jobs by several times. So to summarize what we have covered here, like we loaded the pre-trained sentence transformer model, and then we have encoded the text into semantic embeddings and compared the similarities between the sentence, learned how to use prompts for like specific tasks, and also understood sequence length constraints and accelerated everything using GPU. So these embedding forms the foundation for like modern NLP pipeline and also for like RAG and GenAI projects, from document retrieval and semantic search to clustering and also recommendation system. See you all in our next tutorial. Until then, this is Agonia. Bye for now. Thanks for watching.